Welcome to RBE1001 Lab 3. This week's Electromechanical Lab 1 is the first of a two-part lab. We're going to be designing and building a robot for a nuclear waste disposal challenge. So in this first week's lab, you're basically going to be adding a line-following sensor to your basebot. It is important that you don't modify the mechanical assembly of your basebot at all during this lab. Before we'll get started here, Lab 3, as you guys have all seen, is basically building the line follower circuit. So the first part is to be able to explain and characterize the use of a photosensor or a photoresistor. We want you to be able to design a circuit that uses a photosensor and a threshold adjustment potentiometer to compare the input signals and flip a digital output either high or low based on the reading from the photoresistor. We want you to be able to develop a program that then utilizes that digital circuit to drive your robot around and basically track a line. We also want you to think about your final project during this stage. You're only about 2 weeks away, and when you come back for Lab 4, you'll basically be competing for the bid list. How well you do on Lab 4 will determine how many parts and what kind of parts you're able to get for the final project. So we want you to start thinking about what you could possibly want and need for the final project. Part 1 of this lab is going to be measuring the photoresistor. When you're measuring a photoresistor, make sure that you remove the photoresistor from the circuit. When you're measuring resistance, the resistor needs to be removed from the circuit so that you don't get resistance from other components. We want you to measure the low light resistance and the bright light resistance. The best way to do this is to, one, hold the light up to a light. You don't have to put it very close, but just hold it up pointing towards a light for the bright light resistance. Then we would like you to basically cover it and shield it from any light source so that it's in complete darkness, and take another measurement of the resistance. You may find varied results depending on the brightness of the light, such as if it's the middle of the day when you do one reading and then the middle of the night when you do another reading. The closer you are to a window, the more the outside light will probably affect your readings. We want you to interpret your results and then move on to part 2. In part 2, we want you to build the actual the line sensing circuit, and we want you to basically place the photoresistor over a black line and over a white line, and then record the voltage you see across the photoresistor. We want you to then describe how the circuit you built works to turn that reading into a digital signal. It's important that you do this in your own words. We realize that you're working in a group, but each one of you will have to hand in a lab sheet, and we expect it to be in your own words and not copied word for word from one of your group mates. Lab part 3. Does the digital input value indicate the sensor is on or off the line? We basically want you to place your robot onto a white surface with a black line, and we want you to see where the signal goes high or low, and then tell us why. We then want you to place your robot on one of the ovals that's out in the other room, and we want you to drive around the field as fast as you can. It's more important that you're consistent in the following labs than it is that you're fast. It's very important that your robot completes the challenge when you get to next week's lab, because if your robot doesn't complete the challenge, you'll basically get a distance. And the longest distance is worse than the slowest time. So it's very important that you have a consistent line follower and not necessarily the fastest. The reason we have the TA and SA and initials here is to make sure that you actually completed the challenge and are able to track the line around the field. It's not so much to make sure that you get a fast or slow time, it's just to make sure that you completed it successfully. As I said before, it's very important that you do not change the mechanical design of the basebot at all. So you can use the sensors, you can use the programming and modify those as much as you want, but not the mechanical assembly. We then want you to talk about how you can improve the hardware or software design to make it go faster. There's no limitation here, it's whatever you can imagine. And then we'd like you to just discuss what your plan is for your final robot's drive line, the number of wheels, how many of them are driven, how big you want your wheelbase, is it wheels or is it tracks, and so forth. And then we want you to include a sketch of your drive line below, so that you're thinking about your final project as you have the information from last week's lab about how to gear your robot appropriately. The next part of this lab is going through the appendix. As with all the labs, there is a very detailed appendix for you to basically go through. If you look through, the first part is making sure that you have all the components that you need to complete the lab. You need 2 photosensors, a comparator chip, basically a breadboard or proto board, along with wires and strippers so that you can make the circuits. All of the wire and strippers are available in the back of the lab, so you can basically take as much as you need. Try not to be wasteful. The resistors are in your kit, and if not, there's also a cabinet in the back of the lab where you can pick up the resistors. We also, there will be between 2 and 4 LEDs in your kit, and I'll get into that in a little bit. And then you'll need 1 mount to basically mount your breadboard to the front of your robot. The first step is the photoresistors, or photosensors. There's basically a brief description of it, and I expect you guys to read through this. As you move on, you'll see this brief description of the comparator. You'll see that we're using the LM358 chip, that it has 2 op amps on board, basically with a connected ground and power rail. So there's just 1 power and ground input, but 2 op amps available for your use. The next step is going to be building the sensor circuit and basically building out the circuit that you need to detect the lines and be able to follow the track successfully. The first step when you're building the circuit is to make sure that you plug all the components in correctly. So on the LM358, you'll see there's a notch at the top of the chip. Basically, you'll see with all ICs or integrated circuits that there's a marking that either indicates pin 1 or the top of the chip, and that they're labeled in a counterclockwise direction around the chip. This holds true for the majority of chips, higher than 90% of them. So you can basically almost always assume that they're going to be counted around the chip in a counterclockwise direction. The second thing that's important to get the orientation right is the photoresistor. So the photoresistor, I'm sorry, not photoresistor, the LED has a flat side on the can. So you'll see the LED here has the anode and cathode, or positive and negative side. There is this flat spot on the can, or the bottom edge of the LED. You need to make sure that that flat edge corresponds to the negative side of the LED. And just for reference, there's the circuit diagram at the bottom. You can see that the circuit diagram basically has the flat line corresponding to the flat line on the edge of the LED. It's very important that you plug in the LED correctly. It's also very important that it's in series with a current limiting resistor. If you don't do that, the LED can burn out. As we move down, you'll see that there is the circuit diagram. We expect you to follow this circuit diagram to the best of your ability. Basically, you should always go from the schematic and try to build your circuit directly from the schematic and not look at any other material. For instance, in this lab, we show a picture of the circuit. This circuit has errors in it. We wired this incorrectly so that if you try to copy the picture directly, you'll basically make a mistake and we'll get to see it. So we really want you to be able to go from the schematic to build a circuit. This will be really important going forward for future labs. You can see with the circuit there's a number of different devices on board. The first one at the top left here is the calibration pot. The calibration pot is like most potentiometers. It has 3 leads. The 3 leads of the potentiometer, sorry to do that in the middle of a video, correspond to the back of an LED like this. So you'll see that there's a power and a ground input, and then there is a basically a wiper in the center pin. The wiper in the center pin will output basically an analog voltage proportional to the voltage that's applied to it and the position of the actual wiper on the resistive filament. The next part you'll see is basically you'll see that there's a 68K normal resistor and then a photoresistor. This will go into the inverting input of the op amp, and basically it'll be a varying voltage based on what the photoresistor sees. You can basically set a threshold with your potentiometer so that when the voltage level changes here, it flips the output of the comparator between high and low. This will then turn on or off this resistor, this LED that's in series with a current limiting resistor. Right here is where you want to connect to your microcontroller so that you can sense the output of the individual line sensors. You'll see on this chip, or on this diagram, there's two sets of numbers here, 5, 3, 6, 2, and 1, 7. Those correspond to the pins on the op amps. So there are two separate op amps on this chip, and you'll have two line sensors. So basically you'll be building this circuit twice using the two different op amps that are available on the chip. Most of you have probably used a breadboard before now, but you'll see that a breadboard is basically a way to create wiring. On this diagram here, you'll see that pins A through E are connected together. So all 5 of these pins in each row are connected together, and each row is independent. The same goes for F through J. There are 5 rows and 5 pins connected together, and each row is independent. On the outside edge, you'll see the rows that are set up for basically voltage rails, the ground and power rail that are connected the length of the board. So all of the ones that follow this blue line are connected, and all the ones that follow this red line are connected for the length of the board. There is no connection between either side of the board, so if you're going to use both sides, you need to make sure you have a wire jumper between the two sides. We want you to build the circuit to its completeness on the breadboard, and you should end up with a circuit similar to this. You can see these small potentiometers, they may be blue, they may be silver, have 3 pins. The outside 2 pins are power and ground, and the center pin is your signal pin. It does not matter which side of the potentiometer is power and which one is ground. All it will do is invert the functionality or the output from the wiper. You do want to try to make sure that your photoresistors hang off the bottom of the board as much as you can, so that they can basically effectively read the line. Down here you'll see the mounting plates for the base pot. We provide these plastic mounting kits. They're made out of acrylic, so they are a little brittle. If you hit them, they will crack. But they're basically there so that you can mount your breadboard effectively and have your photoresistors going through the bottom. If you want to take electrical tape and cover the clear sheet, or if you have a black sheet, it's fine, to basically block out any outside light sources, you can. Outside light sources basically cause a little bit of error on these robots, and if the photosensing resistor moves in and out of shadows, you'll basically see that it may mess with your results. There are a few different ways to combat this issue. One is to add an effective shield. The other one is to basically add your own light source. So I mentioned there are 4 LEDs in your kits. There are 2 regular LEDs that are a color, and then there are 2 clear LEDs. They may be red, they may be blue, but they're super bright LEDs. And you basically can use these as flashlights to basically wash out any ambient light that you're seeing from your surroundings. As I said before, make sure you use a current limiting resistor between your power and ground rails when you hook up this LED. But they'll basically act like a flashlight and wash out any of the outside light sources so that you get effective results. As you complete the circuit, you basically need to connect it to your Arduino with a set of wires. You need to make sure you provide 5 volts, ground, and both signal pins to the Arduino or the microcontroller so that you can read those digital outputs effectively. If the ground connection isn't made, you will not be able to basically power the circuit, and you also won't have a reference for the digital output, so it won't read correctly. So ground is basically a reference, and it's important that all of your circuits, or all parts of your circuit, share the same reference so that the signals are read properly between them. The last part is once you have it wired up and you're done electrically, it's time to start programming your robot. There are a number of different ways to do this. You could do it with a case statement, you can do it with just if statements, and we recommend basically writing your own functions for doing the line following and placing that into your main loop. The main thing with code is to make it readable to outside sources, so writing multiple functions that are reusable is always a good idea. Once you've completed programming your robot and you think it's responding effectively to the light sensors, it's time to bring it out to the field and time your robot. Remember, consistency, not speed.